Okay, so what we're going to do now is I really want to argue that this boxed equation over here is an extremely important property of the theory. So let's see why that's so important. Okay, so the first thing that I want to remind you of is the probability interpretation of quantum mechanics. So what we usually do, so let's just talk about quantum mechanics now. We could have a very similar discussion for quantum field theory, but it's identical, and the discussion for quantum mechanics is simpler. If we have some initial wave function psi of naught, and we calculate the overlap with the state n, then the mod squared of the overlap of psi with state n is the probability to catch the particle in state n. That's how we interpret it. And one of the things that's very important for this interpretation to make sense is that our initial wave function over here must be normalized to 1. So that must be 1. And this is needed for the previous equation to make sense. This is the statement that the sum of all probabilities is equal to 1. Okay, so this says sum of all probabilities is equal to 1. So I think that you will have seen that in your quantum mechanics course. If you haven't, go find a nice textbook to read that up in. Okay, we need the state to be normalized so that the sum of all probabilities is equal to 1. Now let's calculate the norm of our state at a later time. So let's calculate the overlap of psi of t with psi of t. Now, we know what psi of t is. Psi of t is just given by taking the time evolution operator and applying that to psi of naught. So if we want the bra psi of t, we just have to take the dagger of this expression. So we've got u of t psi of naught, and we'll take the dagger. So the dagger will reverse the factors. It'll change the ket into a bra, and it'll change u of t into u of t dagger. And now we can use this equation that we're trying to argue is so important, that u dagger of t is equal to u of minus t. So this is bra psi of naught times by u of minus t. So that our overlap then becomes psi of naught, u of minus t, u of t onto the ket psi of naught. And what is this equal to? Well, look what happens here. The first factor of u of t evolves us from t is naught to time t, and then the second factor will evolve us back to t is 0. So the effect of both of those unitaries together is that we get psi of naught and then psi of naught again. The first unitary evolves us to time t, the second evolves us back to time 0. And now we can use the fact that psi of naught is equal to 1. So we can see that this normalization of the state is preserved as long as time evolution is unitary. So the unitarity of time evolution is necessary for the probabilistic interpretation of the quantum theory. It's necessary both in quantum mechanics and it's necessary in quantum field theory. Okay, maybe just another comment. It's obvious that this equation is true. So what are we actually using? Using the fact that u of minus t times by u of t is equal to 1. And if you remember, u of minus t was e to the I ht. U of t is e to the minus I ht. The Hamiltonian is the only operator appearing in this equation, so we can freely add the exponents. We get e to the naught, which is indeed just the identity. So what is the important point? So time evolution is unitary. This is required for the statement that probability is conserved. And we certainly don't want to give that up. So we're going to continue requiring that our time evolution is unitary, and that'll mean that probability, that'll mean that the state is normalized at any time. Okay, so now let's move to Euclidean space. So now move to Euclidean space. Euclidean space. Good. And what we're going to do is we want to again find dagger. So what is dagger? And let's call this equation over here, let's call this equation star. So the fact that u of t dagger is equal to u of minus t, that's an important equation. So I'll say star is our guiding principle, is our guiding principle. Good. Okay, and now denote the dagger denote the dagger in Euclidean space by star. I just want to distinguish the dagger in Minkowski space from the dagger in Euclidean space because they are slightly different. And let's talk about a few more things related between Minkowski and Euclidean. Euclidean time is equal to IT. So this is Euclidean time. So that's Euclidean time. And T is Minkowski time. That's Minkowski time. Good. In Euclidean space, what would u of tau be? U of tau would just be e to the minus. Now remember, in Minkowski space, we've got e to the minus iht. Now it becomes tau, so that in Euclidean space, we've just got e to the minus h tau. Good. Now, what do we want? Okay. This is what we want. We want u of tau star, so the Euclidean dagger, we want this to be u of minus tau. In that equation, this is where we use our guiding principle. So that's telling us what the Euclidean dagger is. If we simply apply the Minkowski dagger, well, we'll get e to the minus, h is equal to h dagger, so h stays the same, and tau is real, so tau stays the same. So u of tau dagger, is equal to u of tau. By the way, can you see that we're not treating the Euclidean theory as an object on its own? The Euclidean theory is something that was derived from the Minkowski theory. So we use the Minkowski theory to set up our Euclidean theory. Imagine the Euclidean theory came from the Minkowski theory. Now, comparing these two equations, we can see that Euclidean dagger of tau is equal to u dagger of minus tau. So this equation tells us how to relate the dagger in Euclidean space to the dagger in Minkowski space. And this is going to be our basic definition. So this is dagger in Euclidean. And we've now got an equation which relates this to the dagger in Minkowski. And this is going to be our guiding principle. What we're going to do next is, what is the dagger in radial quantization?